Right, so welcome to lesson 3 of your unit of electricity, and today's lesson is on series and parallel circuits. Series circuits we've touched on a little bit already, and what we're going to look at today is the ideas about series circuits from previous lessons and compare them to parallel circuits and see if we can spot the differences. So a little bit of spec information there. Start to begin with, please, by having a look at the knowledge check for this lesson. First 8 questions. Pause the video now, look over your notes, look over any other resources you've got, and simply have a go. Right, hopefully you've done that and you've unpaused the video and you want the answers. So if we just get rid of this, you'll see the answers below. Identify the symbol for electric current. I is the symbol we use. The circuit symbol for thermistor, thermal resistor. Circuit symbol for an LED, a light emitting diode. And draw the circuit symbol for an LDR, a light dependent resistor. The arrows going in show that it responds to light that it's exposed to. And the unit of charge, the unit of electrical charge, coulomb. What's the symbol for that? A Q. Compare the current in different parts of a series circuit. So if you think from our previous lessons, the current is the same in all parts of a series circuit. And finally, you've got the symbol for a variable resistor. Right, so just underneath you'll see a brief paragraph just summarising a couple of ideas we've talked about on series circuits already. So it says, in a series circuit, all the current must go through each component as there is only one path to follow. So, if you remember, just in terms of the language we need to be familiar with, current is describing the flow of electrons moving past a point per second, so how quickly those electrons are moving, and must go through each component. So components are things in a circuit, so e.g. a bulb, just as one example of a component. And there was only one path to follow. The potential difference, which is the force that moves electrons around the circuit, is supplied by a battery or a power source. Remember, batteries are made up of multiple cells. And this potential difference pushes the electrons around the circuit. The potential difference is shared between the components in the circuit so that the voltage supplied by the battery is used in the circuit. So if you think about just a simple circuit we looked at before, if you imagine, for example, we have a battery that supplies 12 volts of potential difference, then if we had 2 bulbs, we could have a bulb at 8 volts and we could have a bulb at 4 volts, and they would be sharing the voltage. So that's just how potential difference occurs within the series circuit. So, checkpoint question. Have a little look at this. Could you answer this yourself? Describe the current in a series circuit. Pause the video and give yourself 30 seconds to come up with an answer. Right, should have unpause the video, so if we have a look at an answer. So in a series circuit, the current is the same at all positions since the charge only has one path to flow through. So the key aspects of that definition is the current is the same everywhere and the charge only has one pathway to flow through, one route. Now, we have looked at a video before on series circuits, and you'll see in the comments below and the description below there is a YouTube link to a series circuit video. So if you want to recap any of the information we've already done on series circuits, pause the video, go click on that link, watch this one, take any notes, and then we'll just review those notes in a moment. Right, if you've done that, you'll have unpaused the video now, and as you'll see, just to summarise those key points that we have looked at in previous lesson already about a series circuit. So they are single loop. They only have one loop. Components are all connected one after another. And the disadvantage of them is the whole circuit stops if just one component is disconnected. So for example, let's say we got rid of that light bulb. The whole circuit would stop and it wouldn't carry electrical charge because there would be a gap across which current wouldn't be able to flow. So current is the same everywhere in the series, whereas Voltage is shared across all the components. So the components, for example, the different light bulbs have different amount of voltage. You add those up to get the total voltage. And the same idea applies to resistances. So each component applies a certain amount of resistance to current, stops it flowing, makes it harder for it to flow. You add up those resistances to get the total resistance of the circuit. So that's just a little summary, just to recap from previous lessons, what we did on series circuits. So, excuse me, I seem to have swallowed my drink the wrong way. If you want to pause the video and just make a copy of any of those notes, feel free. Right, if you've done that and you've unpaused the video, we can now look at parallel circuits. So, in a parallel circuit, there are two or more pathways by which the current can flow through the circuit. This means current will split at a junction. So, for example, junction P in the circuit below. Current will split and be shared down those two pathways. It'll then come back together at point Q. So this means that the potential difference in the two branches of the circuit must be the same, as they have the same start and end points. So if you were to measure the voltage across either bulb, you would see that they were the same because they have the same start and the same end points. So, describe the current in a parallel circuit. How would we describe that? In a parallel circuit, the current is shared between different branches. That's the key bit. When the charge reaches a junction, it splits. So, let's spend a little bit more time looking at parallel circuits. So you'll see in the description below, there is another video link to one on parallel circuits. I'd like now to pause this video, open up that link, and watch this one and just make any notes on your notes page or in any revision books, just looking at some of the key aspects of parallel circuits. Pause your video and do that now for me, please. Right, okay. Should have done that, so you'll have unpaused the video. And if we just summarise some of those ideas about parallel circuits. So, thinking about it a little bit more in depth. So parallel circuits have got more than one loop. And each loop generally contains a single component. That's not always true, but generally. So for example, each loop here contains one bulb. Now they're more useful than a series circuit because if one component becomes disconnected, so we get rid of that light bulb, the current can still flow around the other loop. So the circuit doesn't stop working. That's an important aspect for a parallel circuit. Just pull that back in. Now, the voltage across each component is the same as the total voltage of the battery. So let's say we have a battery voltage of 6 volts. That means the voltage across the bulb would be 6 volts. And that means the voltage across this bulb would be 6 volts. And we represent that with our equation. V total, which would be our total voltage of the battery, equals V1, which would be our first bulb, equals V2, equals so on, depending on the number of components we've got. Now, current is slightly different. Current is shared across each of the components. So if we had a total, let's make this up for a moment. If we had a total of If we had a total of 6 amps as our current, we could share it 3 amps and 3 amps across each component, each bulb here. It could be 4 and 2 or 5 and 1. So we know that they're shared across each of the circuit components. So our total for current would be I total, would be I1 plus I2, and so on and so on. Now, the way the current splits depends on the resistance of each component. So we might have 2 bulbs and one bulb has 4 amps of current, and the other has 2 amps of current. Now, the one with 2 amps of current would have a greater resistance because it's making it harder for the electrical charge to flow through it. So therefore it has a lower current. So different components can have different resistances, and that determines the amount of current that flows down each of the pathways. And then finally, resistance. The more components added in parallel, the lower the total resistance. So the key thing here is the more loops, so if we just go back up here a minute, think of this as one loop, think of this as a second loop. If we added a third loop on and a fourth loop on, we lower the total resistance of the circuit, because you are giving more possible routes for the current to flow down. So the current could flow around circuit 1. It could flow around circuit 2. It could flow around circuit 3. So because it's got different routes for it to flow around, it makes it easier for it to move around the entire circuit from our positive to our negative terminals on our circuit diagram. So those are the key aspects of a parallel circuit. So I'll just zoom out a little bit and pause the screen for you there for a moment if you want to add any of that to notes that you've already made. Right, if you've paused the screen, done that, great, brilliant. We'll now move back to looking at some of the rules. So there are rules that you need to know about series and parallel circuits and how components are connected. So they're summarised here, but these can be quite confusing to try and understand, so I've simplified them for you in a moment. So the rules for series circuit, there is always the same current in each component. The potential difference of the power supply is shared between the components. And the potential difference of cells in series is the sum of the individual cells. So you add up the voltage of cells to get the total voltage. And then for components connected in parallel, the potential difference across each component is the same, whereas the total current through the whole circuit is the sum of the currents through the separate components. So that's a little bit confusing. So have a look at this. You might want to copy down this table to confuse it, to not confuse it, make it simpler. In a series circuit, the current is the same across all components, whereas in a parallel circuit, it's shared across all components. Whereas voltage in a series circuit is shared across all components. And parallel, in a parallel circuit, the voltage is the same across all components. So what do you know? These are the 4 rules to really think about. And if you can remember one, they are the opposite of each other. That's how to remember both of them. So it might be worth making a note of that if you didn't quite understand those rules written as bullet points. Right, okay. Once you've screenshotted that and made your own notes on that, let's go back to our question at the bottom here. So, if you feel you need a little bit of support on that, take 2 minutes now, pause the video, and read the circuit rules above, read them in the table, and then close the book and somewhere self-quiz and see if you can remember them. How many of those rules, or can you write out that table from memory? Once you've done that, move on to this checkpoint question, which says, how does the potential difference across the 2 components vary when connected in series and parallel circuits? So, how does potential difference vary? In a series circuit, it's shared across the components. In a parallel circuit, it's the same across components. So we have a look at our answer. Its total potential difference is shared, as we've just said. For a series, potential difference is shared. And in a parallel, potential difference is the same. Good. Right, now let's see if we can apply some of these ideas. So, there are 3 questions here that I'd like to pause the video and now have a go at yourself, and then we'll go through the answers in a moment. Right, you should have unpaused the video, and now if we have a little look at the answers ourselves. So, each cell provides a potential difference of 1.4 volts. What is the total potential difference provided by the 4 cells in the circuit? Total. 4 cells, each provides 1.5. What do you reckon you need to do? 1.5 volts. And you've got 4 cells. Just times it by 4. Would mean the battery up here gives 6 volts in total. Now, what will the reading be on the voltmeter? So here we've got our voltmeter. Now we've got 1 pathway, and we've got 2 pathways. So that makes it a parallel circuit. So if we're thinking about voltage in parallel circuits, let's go back to our rules. Parallel, voltage, the voltage is going to be the same. So let's go back. What will the reading on the voltmeter be? Now, we know what the total potential difference is. We know it's 6 volts. So if it's the same across all components, what do you reckon that makes this? 6 volts also. Well done. And then current through the lamp is 0.2 amps. The current through the resistor is 0.1 amps. What is the reading on the ammeter? So what's the reading on the ammeter? Now, this is a parallel circuit and it's asking us about current. So go back to our rules. Parallel circuit, and it's asking us about current. Parallel, current shared. So it's shared across the components in each of the branches. So for the bulb, it's 0.2. For the resistor, it's 0.1. So what's it going to be in total? 0.2. It's going to be added 0.1. Should be 0.3 amps. Let's see if we're right. There you go, 0.3 amps. Good, starting point. So have a look at the next set of questions here. So, 2 aspects. 1, the table gives the current through 2 of the ammeters. Complete the table to show the current through the other 2 ammeters. So the table gives you ammeter 1 and ammeter 2. It also gives you ammeter 3 by accident. Oh well. So what is ammeter 4 going to be? Bearing in mind, this is parallel. And then have a go at the true and false. Pause the video and have a go at those for me now, and then unpause and we'll go through the answers in a moment. Right, good. So, if we look at this first, what did you get for your answer for ammeter 4? Did you get 0.5? Now, this is parallel. So, what do we know about current? Current is shared. So we'd have 0.5 here, 0.2 here, 0.3 here. If you add those together, when they come back and rejoin, you end up with 0.5. So that's why it's 0.5. And then underneath, you should have your trues and falses, some of it recapping work on energy as well. So true, false, 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 true, true, false, false. Good, right. Now, last little bits for me. So, go on to the next page. So there are a selection of questions here I'd now like you to have a go at. Pause the video, see how many of them you can do, then we'll go through the answers. Good, right, unpause. So, let's go through them together. If A1 measures 4 amps, A1 measures 4 amps, and A2 will measure 2 amps, what will A3 measure? Now, if you remember, our current is coming down here, and it splits. So we've got 4 amps here, we've got 2 amps here. What's that going to be? If it's split and we've used up 2 amps, we're left with 2 amps. If V1 measures 5 volts, what's V2 going to measure? So remember, in this parallel branch, current is shared, which means voltage should stay the same. So if we've got 5 volts here, we should be left with 5 volts. So that's because voltage is the same across components in parallel. Right, and then 2 definitions. Series circuit, 1 pathway for the current to flow down. Parallel circuit, more than 1 pathway. And also, why are voltmeters connected in parallel, if you had to go at that? So a voltmeter is a device used to measure potential difference. Components in parallel experience the same potential difference. It follows that in order to measure the potential difference across a component, we must connect it in parallel. Right, good. So if you've had a go at those, the next thing I would like you to have a go at is some further practice questions. So I'm going to display these questions on the screen. What I'd like you to do is pause the screen and have a go at these questions. So you are identifying if each of these is an ammeter or a voltmeter, and what might the readings be, using ideas that we've talked about already. So pause the screen, have a go at those questions. Same idea here. Pause the screen, have a go at these questions, please. And then final question. Pause the screen, have a go at these questions. And once you've had a go at as many of those questions as you can, so 5, 6, and 7, I'll just pause the screen there so that you've got everything on one screen if you want to keep it on screen at once. Please mark the answers here. So here are your answers for you. So pause the screen, have a look at what you've done, identify if you've got each of these voltmeters or ammeters correct. Good. Once you've done that, come back over here. If there was anything in the lesson today that you weren't sure about, do have a look at the summary videos in the descriptions below. Watch them, make any notes that you feel you need to.